Right now I will give an overview of the components that are typically involved in lossy image data compression. In the rest of the presentations, I will give a brief introduction to each of them. Let the original image be a natural color image, like the Lena image I showed you before. First, the RGB image is converted into a different color space to reduce redundancies between the color channels. Then, redundancies within each individual channel are reduced by deploying a so-called decorrelation transform. The resulting coefficients are then quantized, meaning that the accuracy of the coefficients is decreased. The so-called rate allocator controls the parameters for the quantization. Finally, the quantized coefficients are described in a compact manner by the entropy encoder, which results in the compressed image. The decompressor or decoder just processes that pipeline backwards. The entropy decoder transforms the compact description into the natural one. The dequantizer transforms that to an estimate of the coefficients. They will then be backwards transformed so that the reconstructed color channels are available. Finally, a reconstructed or decoded image can be created by applying the inverse color transform. Note that all steps except of quantization and dequantizations are lossless, at least if we ignore the rounding errors. The first thing that is typically done is to remove redundancies between the color channels. A transform that turned out to fulfill that purpose is the conversion of the RGB to the YCBCR color space. Instead of describing the intensities for three different prime colors red, green and blue, the YCBCR color space describes the luminance in the Y channel and the deviation to that for the colors red and blue. The result is that less information is spread among the channels, which reduces redundancies. On top of that, it is also suitable to human perception. The human's visual perception is a lot more sensitive to luminance than it is to chrominance. This effect can be exploited by eventually describing the chrominance channels CB and CR a lot coarser. JPEG addresses that by typically reducing the resolution of the chrominance channel. And here is how that transform is computed. It is basically just a matrix multiplication. The result will then be shifted to ensure that the values are within a certain range. Since the rank of the matrix is full, it can easily be inverted to create the inverse color transform. The grayscale images you see here show the intensities for the red, green and blue channel like they are in the original image you can see at the very left. As you can see, the images of all three channels look pretty similar. Just the overall brightness seems to be different. This certainly is a penalty for efficiently describing that image. Let's take a look at the YCBCR decomposition of the same image. Here, all three channels look quite different. The Y channel contains all the structural details, whereas the other channels simply describe the color. As you can see, they contain lots of pretty homogeneous regions. From now on, we only deal with one single component of a color image, or with the grayscale image. Let me try to give you a clue of why correlated data is so bad for image compression. Remember that artificial image where each pixel was assigned a random intensity. Now enumerate all the pixels from the top left to the bottom right and put adjacent pixels pairwise together in a two-dimensional vector. The first component of that vector contains all the pixel intensities at even positions, whereas the second component contains all the pixel intensities at odd positions. The diagram you can see now shows all those vectors. As you can see, there is no pattern, and both the values on the x-axis and on the y-axis cover the entire space. Now I did the same thing for the natural image Lena. Still, both the x and the y-axis cover most of the entire range. But the huge difference is that this time the data is highly correlated. If you have high intensity for an arbitrary pixel, the adjacent pixels are very likely to also have a high intensity. But how can we take advantage of that in terms of compression? A simple transform, namely the rotation of -45 degrees, helps a lot. We still don't know anything about the even values, but all the odd values are now very likely to be small numbers. As stated at the very beginning when I was talking about lossless compression, The more we know about an image, the more efficient we are able to describe it. What we did here is referred to as energy compaction, because the energy of the image is now concentrated in the even pixels rather than spread amongst all pixels. Let me now give you an example of the transform that is used in JPEG to decorrelate data. The discrete cosine transform, or simply the DCT. Say we want to encode the sequence 6477, which is shown in the plot you see. The most natural way to describe is to simply store that sequence as it is. However, there are other ways to describe it. For example, as the sum of cosine functions of different frequencies and amplitudes. We can play around a little bit to eventually figure out the different amplitudes of the cosines so that the sum of them go through all 4 points. For this sequence, that is 6, -1.47, 1, and 1.69. Basically, those values tell you how much of a certain frequency is contained in the sequence. The first value, here 6, is simply the average of all elements of the sequence, or if you can express it more complicated, it is the amount of zero frequency contained in the sequence. Therefore, that coefficient is called the DC coefficient, which is in electrical engineering stands for direct current. Respectively, all other coefficients are called AC coefficients. Of course, there are ways to compute those coefficients, but we don't want to discuss that here. It turns out that we need exactly as many different amplitude coefficients for the cosine functions as we had elements in the sequence. The transform can be inversed by simply evaluating that overlay of cosine functions at the various points. Here are some basic properties of the DCT. For natural images with lots of correlation, it concentrates the information mostly in the DC coefficient. All other coefficients usually remain small and therefore can be efficiently described. Besides those desirable properties, the DCT does not address the following points very well. Number 1. Very fast algorithms that compute the DCT coefficients are only available for small sets of data. Thus, it is not desirable to apply the DCT to an entire image. Number 2. Correlation usually only occurs locally within a certain neighborhood. However, an intensity value in the top left corner of an image is pretty much independent from the intensity value in the bottom right corner of that image. Number 3 is that the frequencies don't tell you anything about the location of that frequency. Thus, you do know how much of a frequency in a dataset occurs, but not where in the image that frequency occurs. JPEG, which uses the DCT for decorrelation, deals with those problems by splitting up the image in blocks of 8x8 pixels that are transformed independently. JPEG 2000 uses a different transform to decorrelate the data, the discrete wavelet transform, or simply the DWT. Instead of using cosine functions, it uses so-called wavelets. Here are 2 typical examples of what wavelets look like. Note that they are different from 0 only in a limited domain. The transform basically computes amplitudes for scaled and shifted versions of one wavelet. This results in the spatial and frequency analysis at the same time. Due to that, no partition into blocks is required. However, the computational complexity of the DWT is higher than that of the DCT. Another big advantage is that the resulting compression error for highly compressed images looks a lot more pleasing than for the DCT. Instead of showing blocks, only some of the sharpness of the image will be lost.